All right, so get ready because today we're going to be diving into some seriously mind-bending stuff. We're talking about frozen stars.
Yeah, these things are wild. They could completely change how we think about black holes and even gravity itself.
You sent over some pretty intense research on this, especially that paper called, get this, Thermodynamics of Frozen Stars.
It's a mouthful, right?
Totally. But hey, that's what we're here for, to unpack it all. So, before we get too deep in the weeds, let's start simple. What exactly is a frozen star? It sounds kind of like something out of Star Trek, to be honest.
You know what it kind of is? Imagine something in space, super dense, so compact that if you saw it, you'd swear it was a black hole. But here's the kicker. It doesn't have a singularity at the center.
Wait, well, back up. No singularity, but black holes have to have singularities, right?
Yeah.
That's kind of their whole deal.
That's where things get really wild. See, this whole frozen star idea, it actually came from thinking about black holes in a totally different way, through something called the collapsed polymer model.
Okay, now you're just using big words to sound smart. Collapsed what now?
All right, fair enough. Imagine instead of a black hole being this tiny point of infinite density, it's actually more like a giant ball of string.
A ball of string, like the stuff we have in our junk drawers.
Well, not exactly. I'm talking about those tiny vibrating strings that string theory talks about. Like, those are the basic building blocks of everything.
Okay, so it's like the black hole is fuzzy instead of being a tiny dot.
Exactly. And that fuzziness, that's what the frozen star idea tries to explain using Einstein's theories about gravity, general relativity. It's like finding a way to make those two ideas work together, the smooth space-time stuff and the jittery quantum world.
Okay, my brain is already starting to hurt. So let's break it down. What's going on inside a frozen star? What's the anatomy of this cosmic fuzzball?
Okay, picture a peach.
A peach. Where are we going with this?
Trust me on this one. The pit in the middle, that's like the core of the frozen star. It's where things get so extreme we need totally new physics to even describe them. Around that, you've got the bulk of the star, like the juicy part of the peach, right? And then on the very outside, there's a thin layer, like the peach skin, that blends smoothly into the surrounding space-time.
Okay, I think I'm getting the cosmic peach analogy here. But how does this explain why a frozen star would look and act like a black hole if it isn't one?
All right, so here's where things get really interesting. So frozen stars, they don't have a real event horizon, that point of no return that black holes have. But the gravity near their surface is still super strong enough to rip apart particles and antiparticles right out of the vacuum of space.
Hold on, are you saying this fuzzy outer layer can actually create stuff? Like matter and energy just poof out of thin air?
It's kind of like that, yeah. You've heard of the Schwinger effect, right? Where crazy strong electric fields can make particle-antiparticle pairs. Well, here, it's the intense gravity of the frozen star that's doing the work. Some of those particles get sucked in, but some escape and fly off as radiation.
So we've got virtual particles popping in and out near the surface, some getting flung away. That sounds awfully familiar, doesn't it? Kind of like what happens with black holes, right?
Bingo. You're getting it.
Yeah.
And it gets weirder. That radiation from the frozen star. It's predicted to have a thermal spectrum, just like Hawking radiation, that faint glow that black holes supposedly give off.
No way! A black hole mimic that even emits something like Hawking radiation. That's insane. But if they're so different at their core, how can they both have this thermal thing going on?
Well, you got to remember, frozen stars are still ridiculously dense and compact. Remember how I mentioned that outer layer blending into the Schwarzschild metric?
You did. To be honest, I'm not entirely sure what that metric thing is, but go on.
No worries. It's basically the math that describes the gravity around a perfectly round, non-rotating object, at least in Einstein's theories. And it just so happens to be the same math that describes a black hole's gravity.
So even though a frozen star doesn't have a real event horizon, it's like it's faking it really, really well because its outer layer matches this Schwarzschild description.
Yeah.
Like from a distance, you'd never be able to tell the difference.
Exactly. They'd look almost identical. And that little detail, that's where things get really freaky, especially when we start talking about entropy.
Uh-oh, the dreaded entropy word. Never met a concept that made my brain hurt more than that one. So, humor me. What is entropy, and what does it have to do with black holes, let alone these frozen star imposters?
You're right to be wary. Entropy is a tricky one. You can think of it as a measure of how much disorder there is in a system. The more messed up a thing is, the higher its entropy. And with black holes, it gets super weird. The more massive a black hole is, the more entropy it's got. But here's the really strange part. A black hole's entropy isn't tied to how big it is on the inside, its volume, but to its surface area. like the area of its event horizon.
Wait, back up a sec. You're telling me that a black hole's entropy depends on how big its surface is. That makes zero sense. It's like saying how much stuff you can fit in a box only depends on the size of the lid, not how deep the box actually is.
I know, right? Totally counterintuitive. It's one of the biggest head scratchers about black holes. But hold on to your hat, because here comes the really crazy part. Frozen stars, even though they don't have a true event horizon, they seem to follow this same bizarre entropy rule.
You're kidding me. This fuzzy ball of string pretending to be a black hole somehow still has its entropy tied to this imaginary surface that isn't really there. How does that even work?
That's wild, isn't it? This paper actually looks at it from two different angles, both starting with that idea that the frozen star's outer layer is mimicking that Schwarzschild metric we talked about. And guess what? Both ways of looking at it, they both say the same crazy thing, a frozen star's entropy. Right. Pretty much the same as a black hole with the same mass.
Whoa. Okay, that is a serious aha moment right there. But, and you know there's always a but, with this stuff, I have a feeling there's a catch coming our way.
You know me too well. And this catch involves some serious physics heavy hitters. Gibbons and Hawking, they had this whole argument, pretty convincing actually, that a regular star, no matter how squished it gets, shouldn't be able to have this geometric entropy thing, this surface area linked entropy like a black hole.
Uh-oh. Does that mean our frozen star theory is busted? Are we back to square one?
Not so fast. The key difference is that Gibbons and Hawking, they were working with normal matter, you know, the stuff we see every day. Frozen stars, though, they'd have to be made of something way more exotic, something that breaks all those normal rules. We're talking about matter that acts in ways we're only just starting to wrap our heads around.
So you're saying we're talking about a star potentially made of the same weird stuff as black holes, that stringy matter that makes up that fuzzy core.
You got it.
Yeah.
It's a lot to take in, I know. But here's another brain bender. Even if this exotic matter exists, how could a frozen star actually form in the first place? It's not like a star just wakes up one day and decides, hey, I think I'll be a frozen star instead of a black hole.
Yeah, that's a good point. There's got to be more to it than that. We can't just snap our fingers and say, poof, frozen star. So how does this work, cosmic alchemy? How does a dying star make that leap from normal matter to this weird, stringy stuff?
It's more like a sudden change, a phase transition. Think of it like water freezing into ice. Imagine. A massive star is collapsing, getting smaller and smaller. It's like it's about to become a black hole, but then
the universe slams on the brakes and says, hold up, let's try something different.
In a way, yeah. Instead of going all the way to a singularity, the matter in the star makes this sudden quantum jump. It's like a shortcut through space-time, called a Euclidean instanton. Imagine you're rolling a ball down a hill, and instead of reaching the bottom, it suddenly tunnels through the hill and pops out the other side. That's kind of what this instanton is like.
Okay, quantum tunneling through space-time. Now you're just messing with me, right? So instead of a big crunch, we get this sudden quantum leap, this instanton thingamajig that turns it into a fuzzy, stringy ball. Not your everyday stellar death, that's for sure. But be honest, how likely is any of this to actually happen? It all sounds, well, kind of impossible.
You're not wrong to be skeptical. The odds of one tiny bit of this collapsing matter turning into a frozen star, astronomically small.
So we're talking lottery-winning odds here.
Pretty much. But here's the catch, and it's a big one. There are a mind-bogglingly huge number of those tiny bits of matter in a collapsing star.
So even if the chances for one bit are tiny, when you multiply that by like a gazillion possibilities?
You got it. According to the math, the total probability that at least one of those bits will make the jump becomes significant, maybe even inevitable.
Whoa, hold on a sec. You're saying these frozen stars might not just be possible, but they could be all over the universe right now, hiding in plain sight. We just thought they were regular black holes.
Exactly. And that's just the tip of the iceberg. There's a whole other layer to this, especially when it comes to the biggest black hole mystery of all. Yeah. What happens to information that falls in? Does it vanish forever, or is there a way out? And what does any of this have to do with our new friend, the frozen star?
You're killing me. I guess we'll have to save those burning questions for part 2 of our deep dive into the world of frozen stars. You know, it's funny how we spent all that time in the first part talking about these frozen stars, but the more I learn about them, the more I feel like the real mystery is black holes themselves.
It's true, right? Frozen stars really make you think about some of the biggest questions about black holes, like that whole information paradox thing you mentioned. It's almost like the universe is playing a game of keep away with information and we're trying to figure out the rules.
Right. So for those of us who might have missed that lesson, can you get us a quick refresher on why information disappearing into a black hole is such a big deal? It sounds like one of those things that only theoretical physicists would even think about, let alone lose sleep over.
Well, you'd be surprised. This problem actually gets at the core of how we understand reality itself. See, in quantum mechanics, there's this really important idea called unitary evolution. Basically, it says that you can never truly destroy information about a quantum system. It might get all jumbled up, spread out, sure, but you should always be able to, in theory at least, retrace its steps. Think of it like shuffling a deck of cards, the order changes, but all the cards are still there.
Okay, that makes sense for cards, I guess. But how does that work with something like a black hole? I mean, things get ripped apart, stretched, crushed. We're talking completely unrecognizable, right?
Yeah, and that's the heart of the paradox. Even if something gets shredded down to its tiniest parts when it falls into a black hole, it's information. The really basic stuff that makes it shouldn't just vanish. It should theoretically be encoded somewhere in the universe, even if it's like ridiculously hard to decipher.
But black holes, with that whole point of no return thing, their event horizons, it seems like they just gobble everything up. Once something crosses that line, it's gone, right? Swallowed up by the singularity, never to be seen again. It's like the ultimate cosmic paper shredder, turning everything into the same homogeneous goop. Information. Gone. Just gone.
Exactly. And that's a huge problem for quantum mechanics, where, like we said, information is never supposed to be truly lost. It's like suddenly the universe decided to start randomly deleting files, and we have no clue what's gone or how to get it back. That's why this information paradox is such a big deal. It's like these two really successful theories, general relativity, that's for gravity, and quantum mechanics, which governs the really, really tiny stuff. They're bumping heads. They both work amazingly well in their own lanes, but when you try to bring them together, things get messy. And this information paradox, it's like the king of messy.
Okay, I'm starting to see why this isn't just some abstract physics debate. It's really about how the universe works at its most basic level. But where do our frozen stars fit into all of this? They don't have true event horizons, do they? Could that be the way out of this information mess?
Now that is the billion-dollar question. And this paper, it throws out some really interesting ideas. Remember that fuzzy outer layer we talked about? How it's different from the classic picture of black hole being this smooth, empty void.
Yeah, I think so.
Well, that fuzziness, that quantumness, that just might be our escape hatch from this whole information conundrum.
So it's not just about the singularity being gone, but about how the boundary between a frozen star and the space around it is kind of blurry.
Exactly. You see, that blurriness comes from something called string scale effects. Basically, it's like the very fabric of space-time. At its tiniest level, it's woven out of these vibrating strings. And because of that, the horizon of a frozen star, it's not a hard line in the sand like we think of with a black hole. It's more like, imagine a waterfall.
A waterfall. Okay, now you've lost me.
Hear me out. From far away, a waterfall looks like this solid wall of water, right? But if you could get up close, really close, you'd see that it's churning, changing. There are gaps, little currents, places where maybe, just maybe, something could slip through. That's kind of what the horizon of a frozen star might be like. Porous, shifting, and maybe, just maybe, leaky when it comes to information.
Okay, my brain is officially tied in knots. You're saying that information might not actually disappear inside a frozen star, that it could leak out through this fuzzy quantum waterfall.
Wild, right.
All right.
But that seems to be what the math is pointing to. One way to think about it is with entanglement. You know, that spooky link between quantum particles that even Einstein thought was kind of freaky. The particles that escape as this Hawking-like radiation, they might still be connected, entangled with the information that fell into the frozen star.
So even if the original stuff that fell in is long gone, scrambled beyond recognition, it's like a ghostly copy, a quantum shadow, is still imprinted on these escaping particles, like a fingerprint, but for information.
Now, that is a great analogy. And the coolest part, this isn't just some crazy guess. The paper actually suggests that frozen stars might line up with something called the page curve.
All right, you and your curves. First, the Schwarzschild metric, the page curve. Sounds like something straight out of a physics textbook, not a casual chat about weird stars. What in the world is this page curve, and why should I care?
Fair question. The page curve is basically a prediction, named after physicist Don Page, about how the entropy of a black hole, or at least something that acts like a black hole, should change as it slowly evaporates because of that Hawking radiation. Basically, it says that the entropy should go up at first, which makes sense, but then, and this is the key, it should start to go down.
Wait, down? You mean instead of just eating information and getting more and more entropic, black holes eventually start spitting information back out, like they had a change of heart and are trying to return what they stole?
That's the gist, yeah. And get this, the fact that the math for frozen stars seems to agree with this page curve idea, this whole information slowly leaking back out thing, it's a pretty big deal. It suggests that maybe, just maybe, frozen stars give us a way to make peace between this idea of black holes evaporating and the fundamental laws of quantum mechanics, which say information can't just disappear.
Okay, I've got to admit, that's pretty neat. It's like the universe found a loophole so it wouldn't break its own rules. But let's get real for a sec. You mentioned this process of information escaping a frozen star would be incredibly slow. Like, how slow are we talking here?
Let's just say it wouldn't exactly be a thrilling action movie montage. Think time scales that make the age of the universe look like the blink of an eye. Seriously, for a big frozen star, we'd be talking trillions upon trillions of years for even a tiny bit of information to leak out.
Okay, so fascinating from a physics perspective, sure, but probably not something we'll be observing anytime soon.
Directly observing it.
Yeah.
Probably not happening in our lifetime, that's for sure. But, and this is where it gets really cool, the paper argues that this slow transition time, this kind of fuzzy pause, when a frozen star forms, it should leave a mark, a measurable mark, on the Hawking-like radiation it emits. Like the universe kept a baby picture of the frozen star's formation, and it's hidden in that radiation.
You're saying that even if we can't see the frozen star itself, we might be able to detect this fingerprint it left behind, a little signature in the radiation that tells us about its crazy birth. It's like cosmic archaeology, but instead of digging in the dirt, we're sifting through particles.
Exactly. And to understand how we could find this fingerprint, we got to dive back into the quantum world for a bit. Remember when we briefly touched upon the number operator for outgoing particles? And how it gets modified in the case of frozen stars?
Vaguely. We were going down a pretty deep rabbit hole there, and I'll admit I'm not sure I totally followed that part.
Yeah, that's a pretty hardcore quantum field theory, even for physicists.
Huh.
To put it simply, the number operator, it's basically a tool that tells you how many particles of a certain type you've got in a given quantum state. Think of it like a cosmic accountant, keeping tabs on all those particles. In Hawking's original calculations about black hole radiation, this operator is what we call diagonal. It means all the different particle types are neatly sorted out, like ingredients in a recipe.
Okay, so we've got our cosmic recipe, everything labeled and accounted for.
Perfect. Now here's where it gets weird. When you add in that transition time for a frozen star, that fuzzy quantum pause as it forms, the number operator, it gets what we call off-diagonal terms.
Time for a reality check. Off-diagonal terms. Yeah, I think we're about to get lost in the weeds here.
I promise we won't get too lost in the math. But basically, these off-diagonal terms mean that the neat separation between particle types, it starts to break down. It's like someone dumped a bunch of spices into our cosmic recipe all at once, and now all the flavors are mixed up.
So instead of a neat recipe card, we've got a cosmic stew going on. Gotcha. But how does this help us understand frozen stars?
Here's the amazing part. According to the paper, this mixing of particles, this entanglement hidden in those off-diagonal terms, it's not random. It's directly related to how long that quantum pause lasted, that instant-mediated transition when the frozen star formed. And remember, that transition time, it's connected to the string length, that super tiny scale where space-time itself is thought to be woven from those vibrating strings we talked about.
Okay, my head is spinning, but I think I'm seeing what you're getting at. You're saying that the very act of a frozen star forming, that leap from normal matter to this exotic stringy stuff, it leaves this permanent mark on the radiation that comes out, like a cosmic birthmark, but hidden in the quantum fabric of the universe.
You've got it. It's like the universe decided to keep a record of that event, encoded in the entanglement of those particles. And this isn't just some random mathematical quirk. It has huge implications for how we understand information, black holes, the whole shebang. But I think we need to take a breather here and save the rest of that thought for the final part of our deep dive into the wacky world of frozen stars.
All right, let's jump back into this frozen star saga. Last time we were talking about how the radiation coming from a frozen star, it's like it's telling a story encoded in the quantum entanglement of those.
Yeah.
What was it again?
The off-diagonal terms and the number operator. Yeah, it's a mouthful.
Right, those things. Like, they're whispers from the birth of the frozen star, clues about how it transformed from normal matter into this exotic, stringy stuff.
Exactly. If we could just figure out how to listen to those whispers, how to decode that quantum signature, it would be incredible. like hearing the echo of the Big Bang itself, or at least the echo of one of these frozen stars forming.
So you're saying each frozen star is like a little time capsule broadcasting its life story out into the cosmos, but in a language we can barely understand.
A perfect way to put it. But you've mentioned a couple of times now that all of this, it's not just theoretical mumbo jumbo. What's the bigger picture here? Why should regular folks who aren't like quantum physics wizards care about this stuff? You're right to ask that. It's important. And it gets to the heart of why physics matters in the first place. It's all about understanding the universe at the deepest level possible. And these frozen stars, if they're out there, they're like little windows into a time called the quantum gravity era, right after the Big Bang. Back then, the universe was so tiny, so unbelievably dense, that even gravity itself would have played by different rules, quantum rules.
Okay, you've used that term a few times too, quantum gravity. I think I get the general idea, but give me the crash course version. What's the big deal with it, and how do our frozen stars connect to it?
So right now, in physics, we have these two really, really successful theories, right? Einstein's theory of general relativity, that's the one about gravity being the curvature of space-time, like a bowling ball on a trampoline.
Got it. Gravity as a cosmic dent.
Exactly. And then you've got quantum mechanics, which governs how tiny particles behave, the really small stuff. Both of these theories work incredibly well, but here's the catch. They don't really play nice together. It's like trying to fit a square peg into a round hole. Quantum gravity, that's the holy grail, the theory that would unite these two giants and finally explain how gravity works at the quantum level.
And no one's been able to crack that code yet. Sounds like the ultimate physics challenge.
Oh, it definitely is. One of the big problems is that to really see quantum gravity in action, we'd need crazy amounts of energy, like way more than we can create in even our most powerful particle accelerators. And we'd need to look at things billions of times smaller than anything we can currently see.
So we're talking impossible to study, at least for now.
Pretty much. It's like trying to study a grain of sand by smashing entire planets together. The tools just aren't there. And that's where our frozen stars come in. If we could find even one, if we could study the radiation coming from it, those faint quantum whispers, we might just catch a glimpse of this quantum gravity era. It'd be like looking back in time, seeing the universe when it was just a baby, and maybe, just maybe, finally understanding how gravity really works at its most fundamental level.
Okay, that definitely makes it more exciting than just some abstract math problem. But hold on a sec. You said earlier that frozen stars and black hole, they're basically twins. They look almost identical. So how could we ever hope to find a frozen star if it's camouflaged out there among all those black holes?
$1,000,000 question, right? And honestly, there's no easy answer. The paper we've been talking about, it says that the difference in radiation between a frozen star and a black hole, those quantum fingerprints, they'd be incredibly faint. Like ridiculously faint. We'd need insanely precise measurements and a really, really good understanding of the physics involved to even have a chance of spotting the difference.
So it's going to take more than just pointing our telescopes at the sky and hoping for the best.
Way more, unfortunately. We'd need to push our technology to the limit, invent entirely new ways of looking at the universe. And yeah, a little bit of luck wouldn't hurt either. But here's the thing. There might be other ways to find them, too. Remember how we were talking about the birth of a frozen star, that sudden quantum phase transition?
Like when it suddenly decides to become a fuzzy, stringy ball instead of a black hole?
Exactly. That process, that sudden shift, it might release a burst of energy. And not just any energy, gravitational waves.
Gravitational waves, like the ripples in space-time that LIGO and Virgo are detecting. Could we actually hear a frozen star being born?
It's possible. Now, these wouldn't be the same kind of gravitational waves that we've seen from, say, black holes merging. The signal from a frozen star would be unique, a fingerprint of that quantum leap, that instant-mediated transition. It would be like listening to a cosmic orchestra and picking out the faint, fleeting sound of a harp in a sea of other instruments.
So we're not just looking for a needle in a haystack, we're listening for a whisper in a hurricane. Sounds difficult.
Difficult is an understatement. It would be a monumental challenge, no doubt. But imagine if we actually did it, confirming that frozen stars are real, maybe even decoding their gravitational wave signals. It would be huge. It would change how we understand gravity, black holes, maybe even the origin of the universe itself.
Wow. It's incredible to think that something as seemingly simple as a star, well, a frozen star, could hold the key to unlocking some of the universe's biggest secrets. This whole deep dive has been mind-blowing. We've gone from fuzzy stars to information disappearing and reappearing to the very first moments after the Big Bang, all in the search for these hypothetical objects.
It's enough to make your head spin, right? But that's what makes physics so amazing, so endlessly fascinating. There's always something new to discover, a new mystery to unravel. And even if we never actually see a frozen star directly, the very act of searching for them, of asking these questions, it pushes the boundaries of what we think is possible. And that's what it's all about, right?
Couldn't have said it better myself. For now, we'll have to keep our eyes on the stars and our ears tuned to the symphony of the cosmos, listening for those faint whispers of truth. Until next time, keep asking questions, keep exploring, and never underestimate the power of a really, really good mystery.